Starting in the cell body, what we are going to assume is that this cell has been previously stimulated by another cell. And we're going to look at the graded potentials that are occurring in the cell body. So what we're looking at here is a depolarization. Okay, coming in, again, another cell has stimulated the cell, and the cell has become less negative. Now remembering that is talking about the inside of the cell with respect to the outside. Assuming that the resting membrane potential is approximately minus 70 millivolts, this depolarization is going to bring it towards zero, making it less negative. This is a graded potential because should the stimulus be stronger, the amplitude of this response would have increased. As it moves through the cell body, what you'll note here is that the amplitude actually decreases. This is known as decremental conduction. Now what we can look at is that another cell has stimulated the cell body, and instead of making the cell less negative, it's making it more negative. So this is hyperpolarizing the cell, taking it away from threshold. Okay? And again, stronger stimulus, larger response, that's what makes it a graded potential. As it moves through the cell body, it will decrease its amplitude. Once again, decremental conduction. The depolarizing responses are bringing the cell closer to threshold and therefore potentially exciting the cell, and that's why they're called EPSPs. The hyperpolarizing is taking it further away from threshold and thus being called an IPSP, an inhibitory postsynaptic potential. I want to discuss the concept of integration. In the cell body, these postsynaptic responses are integrated. Here, for example, we have an EPSP and an IPSP. These two things are going to add up together. In effect, what's going to happen is one's going to cancel out the other. However, these responses could be varied. If we had a very large EPSP, this IPSP may not cancel out the EPSP. They're added together. We'll discuss later on the concept of spatial and temporal summation, but at this point just realize that the integration is occurring by adding up all of the postsynaptic responses. These graded responses then travel to the area of the neuron known as the trigger zone, or right here, the axon hillock. At this point, there's going to be a large concentration or high concentration of voltage-gated channels. And in particular, we are looking at the voltage-gated sodium channel and the voltage-gated potassium channel. Okay, remembering the concentration gradient for these two ions, sodium is going to be higher on the outside of the cell and potassium is going to be higher on the inside of the cell. So given the chance, if these channels actually open up, okay, the gates open, sodium will be allowed to move into the cell and potassium will be allowed to move out of the cell. That is the reason that the graded potential from the cell body can trigger an action potential. It's because there's a high concentration of these voltage-gated channels at that location in the cell. Taking a closer look at the voltage-gated sodium channel, you'll note that there are two gates. There is an activation gate and an inactivation gate. At rest, the activation gate is closed and the inactivation gate is open. But as long as one of these gates is closed, sodium is not going to be able to move down its gradient into the cell. Note at rest that the voltage-gated potassium channel is also closed, so potassium is not going to be allowed to move down its electrochemical gradient. In order to generate an action potential, this sodium channel has to open up, and that is what's going to happen in response to the summation of the graded responses coming in from the cell body. If this graded response, after all the temporal and spatial summation, reaches the threshold, there will be enough of these channels, these voltage-gated sodium channels opening up, in effect this activation gate opening up, to allow sodium to come into the cell. So let's take a look now what happens, assuming that the graded response coming in from the cell body has reached threshold. You can note here that the activation gate of the sodium channel, this voltage-gated channel, has now opened up. This is now going to allow sodium to move into the cell. What that is going to do is make the inside of the cell less negative. And you can see up at the top here that this is going to account for the upstroke of the action potential. Okay, as the sodium moves in, the cell is going to get less negative, it's going to depolarize, and the upstroke of the action potential will occur. Note that these voltage-gated potassium channels also start to open up. But as I've tried to indicate here, that they're opening up very, very slowly. So not a lot of potassium is going to actually be leaving the cell. The amount of sodium coming in far outweighs the amount of potassium that may be leaving at this point. Approximately 0.5 milliseconds, which is about the time that we have right here, the upstroke of the action potential is stopped, and that's where we reach the peak of the action potential. And this is because, as you can see here, the inactivation gate of the voltage-gated sodium channel closes. Sodium now cannot continue to move into the cell. The other event that's occurring simultaneously with this is that those voltage-gated potassium channels, even though they've been slowly opened, are now opened, which now allows potassium to move out of the cell. So this is now going to account for the repolarizing phase of the action potential, or the downstroke, because this positively charged potassium is going to make the inside of the cell more negative by taking positive charge out. Once these inactivation gates close, okay, approximately a half a millisecond after the activation gate opens, they remain locked, which means that you cannot generate another action potential at this point because you cannot get those gates opened. During this period, okay, it's called the absolute refractory period. So again, that is due to these inactivation gates being locked closed. These voltage-gated potassium channels were slow to open, and they're also slow to close, which means that potassium is going to continue to move out of the cell, and this is what accounts for the hyperpolarization, or the undershoot of the action potential. Okay. During this time, I just want to pay attention here to the positioning of these gates in the voltage-gated sodium channel. They're resetting themselves. The activation gate is now going to close again, and the inactivation gate opens. This is resetting these channels. Until these channels are reset, again, you're not going to be able to generate an action potential. If you have a stronger than normal stimulus, you may be able to activate enough of the channels that have already reset to generate an action potential, but you'll need a higher than normal stimulus because a lot of those channels have not reset themselves yet. One other thing to note here is that these action potentials are all or none, meaning they will be at their full amplitude or not at all. Whether an action potential is elicited or not depends on the graded response. If it reaches threshold, you will get the full blown action potential. If, however, it is sub-threshold, you will get nothing. There will be no action potential generated. Remembering that the cell body is the site of integration. The purpose of these action potentials is just to communicate information down the cell to communicate with the next cell. The sodium that came in from the previous action potential then diffuses within the axon. So here we're showing that the sodium is diffusing, and this is known as the local current. As it diffuses, it's going to make the adjacent area of the membrane less negative. That is a depolarization. At this point, it will then trigger these voltage-gated sodium channels to open up. In particular, that activation gate that was closed will now be open. More sodium will then move in and diffuse to the next area of the membrane. Note here that we have the myelin sheath. Okay, what is happening here? What's happening here is that this myelin is insulating the axon. Remembering that in the CNS it is oligodendrocytes, in the PNS it is the Schwann cells, and it does not allow for the movement of ions. So the action potential is going to jump from one node of Ranvier to the next. And again, those nodes of Ranvier are just the spaces in between the myelin sheath. Okay, this is known as saltatory conduction. The propagation is simply the movement of these, or the triggering of one action potential after another going down the axon. And note here that there is non-decremental conduction. Remember, with the graded potentials, the amplitude would decrease as it's moving through the cell. With the action potentials, they're going to be of exactly the same amplitude at every spot along the axon. There is one-way propagation of action potentials, and that's away from the cell body. As the sodium moves into the cell, it will diffuse in both directions, however. So the question is now, why do the action potentials not go backwards? It's because this area of the membrane is in its refractory period, so you are unable to elicit an action potential in the opposite direction. At the axon hillock, there will be sodium that also diffuses back into the cell body. However, there's not enough voltage-gated sodium channels to elicit an action potential in the cell body. So there's going to be saltatory, non-decremental conduction, okay, propagating one way away from the cell body. I'm going to continue the rest of this story in another video.